Welcome everyone to lesson 3.12 from Precalculus, which is all about equivalent representations of trigonometric functions, aka trig identities. So let's get started. So let's recall from before that an identity is a math statement that's always true. We have used a couple of those in the past, but we're going to mainly focus, we're focusing today on trig function identities. So we have quite a few, so bear with me. And we're going to talk about each and every one of them from the beginning. So last class, we talked about the reciprocal functions. These reciprocal functions are also part of identities called the reciprocal identities. We can rewrite sine as 1 over cosecant, cosine is 1 over secant, so on and so forth. We can use any of these identities, and they're true for every value of x except for when you divide by 0. So keep that in mind. You cannot divide by 0, so the denominator cannot equal 0 for any of these. But besides that, they are identities. Quite interesting. Then you have the quotient identities. We can rewrite tangent and cotangent in terms of sines and cosines and a quotient thereof. Again, can't divide by 0, but these values, like whatever causes the left to have a problem, causes the right to have a problem, so that gets cured in this case. So we've used all of these previously, nothing new there, nothing to worry about. Everything is fine and dandy with the world. The new one we're going to talk about is the Pythagorean identities. So Pythagorean theorem, if somebody sells that to you, you probably have it tattooed on your brain, a squared plus b squared equals c squared, right? The sum of the two legs squared equals the hypotenuse squared. We're dealing with the unit circle. So if I zoom in on this unit circle, any point on the unit circle, we can create a right triangle with the x-axis. And in doing so, the leg that touches the x-axis is equivalent to the cosine of the angle, and the leg that represents the height of the triangle is equivalent to the sine of the angle. And the hypotenuse is always 1 because the radius of the circle is 1. So if we build a Pythagorean theorem from this, we end up with sine squared plus cosine squared equals 1, or cosine squared plus sine squared equals 1. It doesn't matter. The order doesn't matter. That is a Pythagorean identity. This is our first one, and it's the one we're going to build the other ones off of. It's fairly intuitive. You can easily pick this up, and hopefully from that diagram, it makes sense to you why that works. Interesting enough, this is also why the equation for a circle is x squared plus y squared is equal to r squared, which we may not already talked about, or we may dive into soon. So that's all fun and dandy. So that's one. I put a plural in there, identities. What are the others? Well, we can get the others by taking this first identity and dividing by either sine squared or cosine squared. If we divide by sine squared, we get the identity 1 plus cotangent squared equals cosecant squared. Conversely, if we divide by cosine, we'll get the identity tangent squared plus 1 is equal to secant squared. And you can take these identities and you can manipulate them. It is 100% a-okay to manipulate identities. What do I mean by this? Well, I mean that if I wanted to, I could say that cosine squared is equivalent to 1 minus sine squared. That is a-okay, and in fact, you will probably have to do this at some point. In addition, we can also manipulate the identities up here, meaning that, for example, if I look at this one, that sine times cosecant of the same angle is equal to 1. So these may come up, and you just have to be, good at putting puzzles together. It's essentially what this lesson is all about. So let's put all of this into practice. Let's simplify some expressions. So, Mr. Whaley tip number 1, if you're not sure where to go, change everything into sines and cosines. So here, tangent, I can write that as sine x over cosine x times cosine x. Well, cosine and cosine cancel. This just turns into sine. This one here, this one looks like a Pythagorean identity. If you see anything that has squareds and ones or addition or subtraction, think this could probably be Pythagorean. So which one uses cosine squared and 1? Well, we have, oh, it did not like me there. We have sine squared plus cosine squared is equal to 1. We technically have variables on those. Well, 1 minus cosine, what happens if I subtract cosine from both sides? I get sine squared x is equal to 1 minus cosine squared x. So I can substitute this value in for the whole numerator. So I get sine squared x over cosine squared x. Sine of cosine, that's tangent. So this is equivalent to tangent squared x. Again, not that bad. Right now, it's kind of blindly putting puzzle pieces together and seeing if they fit. Rule of thumb for these is you're trying to essentially try to get it down to a singular trig function. So down to sine, down to tangent is a good indicator of I've done this the way I should, or where to stop. This one here actually is the sine squared plus cosine squared, just rearranged. So this is 1 over sine x times secant x. Well, let's split this fraction apart. We have 1 over sine x, and 1 over secant is cosine times cosine x over 1. Cosine over sine is cotangent. So there we go. So all of these got broken down into a singular trig function. It might be squared or something like that, but I digress. That's usually the stopping point. Sometimes you might get one. Sometimes you might get more than one thing. Every one of them is very different, and that's why a lot of students get very frustrated with this unit, and specifically like trig identities. Don't drag your heels. Don't fall into a I can't do this kind of mindset. You can, and here's a couple of strategies to help you out, especially to start. So if you're not sure where to start, if you have powers, it's probably a Pythagorean identity. Otherwise, I say, if in doubt, sine and cosine it out, convert everything into sines and cosines. And in doing so, you might see the pieces come together. You're essentially looking for those puzzle pieces that mash together and cancel each other out. Why do we need identities? Why learn all of this stuff? This just seems like math mumbo jumbo. It might be nice to talk about. It might be pretty, but I'm an applied math person. Where am I going to use this? We can actually use this to solve equations that would have been impossible otherwise. So let's look at the first one here. 1 equals secant squared plus tangent. Secant and tangent don't play together. But you might be in the mindset of, how do I get all of this to be the same trig ratio? If I can get this to be the same trig function, it's doable, right? We've solved quadratic style equations before, but they were always the same trig function. It was always all sines, all cosines, all tangents. This one's not the case. Can I write it like that? And if that's where your mind goes, is can I write this all as one trig ratio or trig function? You're thinking like a mathematician. So this here is squared, right? One of our trig identities is tangent squared x plus 1 is equal to secant squared x. If you don't believe me, we can scroll up. Tangent squared plus 1 is equal to secant squared. So we can replace the whole secant squared with more than one term. We can do that. That's perfectly fine as long as we maintain the equivalence. So that means if there was a coefficient, we would have to distribute it. But we can rewrite this as 1 equals tangent squared x plus 1 plus tangent x. We can subtract 1 from both sides, and we get 0 is equal to tangent squared x plus tangent. We can factor out a tangent, and then we can get something to work with, right? So we get 0 is equal to tangent of x, or when I factored it out, I would have had tangent plus 1, subtract 1, or tangent of x is equal to negative 1. I can solve those. I can do that. Where's tangent 0? Well, tangent is 0, 1, undefined, negative 1, 0. So It's whole values of pi. So as far as we have a restriction on, it would be x is equal to 0, pi, and 2 pi, right? -1, not coming to me as quickly. -1, negative slope. That would happen here and here. And the increments would have to be the same. So 45, 45, 90. So this would be 3 pi over 4 and 7 pi over 4. And then we have our answer. So that's not bad. What you do have to keep in mind, though, and what some people might not point out to you, and I've made the mistake before, you have to make sure that we're not dividing by 0. What do I mean? Secant is cosine of x in a denominator, right? So anywhere that this would be 0, we'd have to exclude. Luckily for us, cosine is 1, 0, -1, 0, 1. So these values are perfectly fine. But there may possibly become a chance where you, again, have to make sure that your answers actually work in the original equation. Sometimes when you do things and manipulate equations, you accidentally introduce extraneous solutions. You just have to double check sometimes. Although if you're doing it quick, like you're rapidly doing it on an AP exam, or I don't think this would be on the SAT. If it's multiple choice, don't worry about it. If it's short answer, I would check just because. Let's look at this one here. Now, I'm going to tell you now a pitfall that I know that some of you are going to fall in. It's sine squared plus cosine squared, Mr. Whaley. But it's not, though. It's not. The sign is negative. There is no identity right now for negative sine squared plus cosine squared. Doesn't work. But if you were thinking Pythagorean, you are on the right track. This is Pythagorean, is it not? We have sine squared x plus cosine squared x is equal to 1. So that means that cosine squared x is equal to 1 take away sine squared x. So this whole piece becomes cosine squared x. Well, cosine squared plus cosine squared is, well, 2 cosine squared. So cosine squared x is equal to 1. Remember, when you take the square root, positive or negative. So cosine x is equal to positive or negative 1. Where does that happen for cosine? On the unit circle, it happens at the tippy top and the tippy bottom, right? So it happens at pi over 2 and 3 pi over 2. And because we're, again, restricting ourselves between 0 and 2 pi, those are the only possible solutions. So x is equal to pi over 2 and 3 pi over 2. No, Mr. Whaley messed up. Oh, no. No. How many of you are yelling at me through the screen? Rightfully so. Mr. Whaley made a mistake. That was sine. Ah, Mr. Whaley, how dare you. Cosine is 1 and -1 at whole values of pi. 0, pi, 2 pi. So Mr. Whaley was very wrong there. 0, pi, 2 pi. You got to yell at me for that one. So, that was some of our basic identities. We do have, there are so many identities for trig. A lot of them we're actually not going to learn. So, if you want to deep dive into them, or maybe we deep dive into some of them in class, forewarning, just keep that in mind. There are so many identities. So, the last two are very, very much related that we're going to talk about. There are, again, so many more. The first one up is the sum and difference identities. Have you ever had an angle and you're like, we can't find this angle by hand? It sucks. Well, we might be able to now. And that's kind of where we are. So if I can write an angle that we don't have a value for, or we do, you could technically do it once you do, but why would you? We can write, if we can write it as a sum or a difference of two angles we know, we actually have identities for that. So if we have the sine of an angle that we know plus another angle we know, we can rewrite it as sine alpha cosine beta plus sine beta cosine alpha. And then we have all of these. So I really want you to do like a notice and wonder right here. Pause the video. What are some things that you notice? What are some things that you wonder about these four? And let's talk about them. So some things that I notice is that a plus with sign is a plus, minus with sign is a minus, or cosine is different. We have a plus and then we go to a minus, we have a minus and we go to a plus. I wonder why that is. I wonder if we can use the sums to find the differences. That might be an interesting exercise there. Something else that I notice is that for cosines, they're bunched up. We have cosine, cosine, sine, sine. But for sine, we have sine, cosine, sine, cosine, where the angles switch. Now, it's important to note that the only one that it really seems like you have to memorize which one's alpha and which one's beta is with sine. So the alpha, the first angle, goes first. The second angle goes second. So it takes a little bit of practice. You're going to have to memorize this one. So those mnemonics of cosine, cosine, sine, sine, or plus is plus and minus is minus, or so on and so forth, or cosine is different. Just got to think of them up. Maybe you have more creative ones than me, and if you do, please share. I'm willing to learn. Let's use some of these identities in practice. So we have sine addition. So sine addition, let's cover that up. Let's not cheat. Sine addition is sine cosine with a plus in the middle. The first angle goes first, and the second angle goes second, and they switch for cosine. Second is first, and first is second. Now, do you have your trig function evaluations memorized? I don't. I do have my right triangles memorized. So pi over 4, that one's really, really easy. Right? 1 root 2. So this is the square root of 2 over 2. This is the square root of 2 over 2. I got that memorized. 5 pi over 3. 1/3 less than 2 pi, so we're in quadrant 4. That's an awful looking triangle. Let's try that again from the top. So we're pi over 3 less than 2 pi. This is medium side, so it's crossing the medium angles crossing the medium side. 1 and 2. We are going down, so this is negative. So the cosine of this would be 1 over 2. 1 over 2. Sine of this would be root 3, negative root 3 over 2, negative root 3 over 2, times plus. So we get square root of 2 minus the square root of 6, square root of 2 minus the square root of 6, all over 2 times 2, which is 4. Not that bad. For a lot of these, especially the ones that are like a pi over 3 and a pi over 4, or a pi over 6 and a pi over 4, you're pretty much going to have root 2 and root 6 over 4 in some combination. Just fair warning. What about this one here? Well, it's cosine difference. So cosine, I know, is cosine, cosine, sine, sine. For this, it doesn't matter, right? So 7 pi over 4, 2 pi over 3, 7 pi over 4, 2 pi over 3, and a minus turns into a plus. What are our two triangles here? Well, let's start with the 7 pi over 4. The 7 pi over 4 is a quarter short of 2 pi, so we're in quadrant 4. So that would be negative 1, 1, and the square root of 2. So cosine would be 1 over the square root of 2, so square root of 2 over 2. The sine, however, would be negative square root of 2 over 2. Now we have 2 pi over 3. That is 1/3 short of a pi, so that's in quadrant 2. Pi over 3. It is the medium angles across the medium side. Negative 1, 2. So for cosine, it would be negative 1 over 2. For sine, it would be root 3 over 2 times plus. So we have negative root 2 minus negative root 6 over 4. So essentially not too bad. Mnemonics help out, but again, however you choose to encode this into your brain, as long as it's encoded, that's all that matters. Let's take this a step further. We know that this is a translation of the sine function to the left by pi over 6, right? That's what this means. Let's see what crazy thing that this is the same as. well, transformation would be the same using sine sum. So again, sine sum is sine cosine with a plus. First angle goes first for sine, and second angle goes second for sine, and then cosine switches, so second is first, and first is second. So it looks like to me I need to find out what's happening with this pi over 6. So pi over 6, 1, root 3, 2. That looks awful, but I'm not fixing it. Cosine is root 3 over 2. So root 3 over 2 sine x plus sine is 1/2. 1/2 cosine x is equal to just shifting the function to the left by pi over 6. I think that's kind of interesting that we can take sines and cosine functions and combine them to just make a regular function. There's numerous applications of this, you could say, like sound waves. You can break apart sound waves into individual like sines and cosine curves. I think this is interesting, and yeah, if you have questions, make sure you ask. All right. Last but not least is the double angle identity. So the last one is we're going to talk about. So for sine, the double angle, if we use sine sum with the same angle, we end up with the identity sine of 2 alpha is equal to 2 times sine cosine. Cosine, though, has quite a few, because doing it by default, just using the cosine sum, we get cosine squared minus sine squared. Interesting. It kind of looks like the Pythagorean identity, but with a minus instead of a plus, right? That's kind of cool. Speaking of Pythagorean identity, since both of those are squared, if you use a Pythagorean identity with a cosine, you get this identity. Or if you use the Pythagorean identity with sine, you get this identity, which I think is really, really cool and has applications in reducing powers for sine and cosine when you do some complicated math with them, which is really, really cool. So before we go any further, if your mathematician brain is going off, where's tangent? Like, where's tangent, Mr. Whaley? We're not talking about tangent here for any of these. That is a wonderful question and foreshadowing to something that we might be doing in class together. So let's use these identities to solve equations. Why else would we use them, right? So sine 2x is equal to cosine, and we want to find all of the solutions between 0 and 2 pi. Well, sine is 2 sine cosine. Now we have to be careful. I can't divide by cosine because there are values of x that cause cosine to be 0. So I need to subtract and factor. So what I'm going to do is I'm going to do that in one step. Cosine x times 2 sine x minus 1 is equal to 0. So either cosine is equal to 0 or sine is equal to 1/2. Those are the two possibilities. We know where those occur. Cosine is 0, 1, 0, negative 1, 0, 1, at pi over 2 and 3 pi over 2. I promise that I didn't mess up on this one. Sine, however, 1/2 happens twice. Again, if you're stuck, draw a circle. 1/2 happens twice. Where does it happen over here? Well, 2 and 1, that would be pi over 6, right? So this has to be pi over 6 less than pi. So that would be 5 pi over 6. So the final answer would be x is equal to pi over 6, 5 pi over 6, pi over 2, and 3 pi over 2. If you want to write those in ascending order, you can. I'm not going to take the time to do that, but you can. What about this one? Now, something I want to note is cosine has 3, right? So you might have to pick and choose which one's most favorable to you. But before you do, make sure you just have one of them memorized. And if you have one of them memorized, I would memorize that cosine of 2x is equal to cosine squared x minus sine squared x. It is the identity that is the nicest to work with, and then you can use Pythagorean identities from there. So because I have a cosine squared on the other side, let's turn this into solely cosine squareds. So I can turn this sine squared, so we have the cosine squared. I can turn this sine squared into 1 minus cosine squared. Distribute the negative, I get 2 cosine squared x minus 1. So I don't have to memorize all three. If I can memorize this one, I can get the others. And this is so much more useful. So now we can plug this into here. We would have 3 parentheses 2 cosine squared x minus 1 is equal to 2 cosine squared x. Distribute 6 cosine squared x minus 3 is equal to 2 cosine squared x. I like things to be positive. Let's subtract 2 cosine from both sides and then add 3 to both sides. So we have 4 cosine squared is equal to 3. So cosine squared is equal to 3/4. And finally, we're getting there. Cosine is equal to root 3 over 2. Where does that happen? Oh, not just root 3 over 2, positive or negative root 3 over 2. So drawing the circle, we have that a couple of times. So we can find one and then use that to find the others, right? So we want root 3, 2, which means the height would be 1. That would be at pi over 6. So then this would be, so if this one's pi over 6, this would be 1 less than pi, or 1/6 less than pi, so 5 pi over 6. This would be 1 more than 1/6 more than pi, so that would be 7 pi over 6, and 1 less than 2 pi, which would be 11 pi over 6. So we have those as solutions. And we write that down, and we are done. So as I hinted at before, we have quite a few different identities to work with. There are a lot, and there are more than the ones that we're covering here, but these are the major ones that are covered on the AP exam. If you want to learn about some of the others, and we don't talk about them in class, you're mathematicians now. Look them up, ask questions, feed your curiosity, and I'll see you in the next video.